Good morning to you all and welcome to this Motec webinar. My name's Dwayne Mitchell and I work in the Motec Operations and Research Centre in Melbourne, Australia. The title of today's webinar is How PDM Logic Operators Work. So today what we're going to discuss is a very quick summary of what a PDM or Power Distribution Module is, just to refresh our memories. Then we're going to look at how we can set these things up to cater for multiple conditions. So we have a conditions setup system that allows us to look at multiple inputs and make decisions based on those inputs. So we use operators, what we call operators, to perform these logical conditions, and then we can combine these conditions in a number of ways. And the last thing we'll do is we'll go through a step-by-step example of how to set up a not terribly complicated, but still a useful example of how to set up some of these conditions to produce a complicated output from a number of inputs. Okay, so a PDM is a power distribution module, and these come in a number of versions, but effectively they all function in a very similar fashion. And effectively what it is a device which feeds power at high current from your battery to the various powered devices that you might normally operate via relays or fuses or other control systems. And the benefit of a PDM is that it can do all this from one device, and it has very sophisticated monitoring and decision-making capabilities, which is of course what we're looking at today. Some of the benefits of a PDM are that it can have electronic fuse control. It can automatically reset these electronic fuses, which means that if a device such as a fuel pump is failing, the PDM can monitor that and can make decisions about whether it should retry the fuel pump to keep the engine running. So the PDM is a very useful device, and of course the main benefit of its usefulness is that you can take signals from various sources, and you can use these signals to make multiple decisions and control multiple devices. So there's a great deal of interoperation between the devices on this system. Okay, so the way we deal with the PDM is via a piece of software which we call the PDM Manager. What you can see on screen is basically the open page when you first run the PDM Manager. Now, like all of our Motec software, the menu structure is quite similar, and you need to open the file that you're working on or create a new file so that you can make what we call a configuration which allows you to operate the PDM. So what you're seeing on this screen is the normal PDM Manager screen, and I've already opened a file which I've called PDM Webinar, and on the left-hand side we can see a list of the input pins, the CAN inputs, and then an entry called conditions, and that's for the one we're going to be concentrating on today. Let's point that out. So up here we have conditions, input pins, CAN inputs, and conditions, and finally output pins there. So one of the examples we'll show you today involves setting up these conditions and then to operate a fan on an output. So what we're looking at with conditions is conditions are a group of operations, and they define how a channel is going to operate. Now the great benefit of the PDM is that these channels or logic channels can be accessed by other logic channels, so you can nest instructions, you can nest decisions. It's quite a complicated structure, and you can choose to use it in a number of different ways. On the right hand side you can see an example, and what we're calling this is just a condition called rear brake light on up the top, and then down the bottom what we have is a list of conditions which need to be met before this function is enabled. Now I won't go into detail about this right now, but what you can see is you can have multiple conditions here listed in order, which combine to form a group or a composite decision. And if any or all of these conditions are met, then the right brake light would turn on. Now, amongst other things, this right brake light turn on condition can also be referenced by other devices because each of these conditions can be used interchangeably with other things as well. Conditions are calculated 50 times a second, which is about every 20 milliseconds in other words. And it should be remembered that a PDM is not a device for running an engine, it's a device for running ancillary equipment such as fans, motors, and so forth. So a calculation time of 50 times a second is extremely fast when it's seen in this context. Okay, so the way conditions are built up, as you saw in the previous screen, is by what we call operators. Now, an operator is the essential basic logic block. It's like a function block. It has an input and an output. And typically the input is something like a switch input or a temperature number from something like an engine temperature. And then an output is a condition like true or false. So we can select which channel we want to go as an input into this condition. And then we have a choice of operators, which is what we call the decision-making component, if you like. Now, there are a number of operators. There are logical operators, conditional operators, time operators, and edge-based operators. Each of these has a use in a particular application, and you can build these into complex functions, as we've said. And normally, operations can be grouped together, which allows us to, again, to construct very complicated logic functions. So on our right-hand side of this screen, we can see a whole list of these operators. And as you can see, there's a true, a false. These are simple basic logic. And then we can get down to making comparisons like equal to or not equal to, greater than, etc. So I'm going to go through each of these in order, and we're going to be able to see just how the interaction works for each of these different types. Okay, so the most useful one we have are logic operators. And if you just look at these tables, it looks a little bit baffling, but it's not actually that bad. The simplest ones are things like true and false. Now, again, as we said, we have an input and an output to each of these operators. So if we look at this true-false one first, it's quite simple. When you have a false input, you get a false output. And when you have a true input, you get a true output. This is fairly self-evident. However, we have a reversed version of the same thing, which inverts the logic, if you like. So if you have a false input, you'll get a true output. And if you have a true input, you'll get a false output. So that's why there are two operators, a true and a false operator. They effectively function in a similar fashion, but one of them is the reverse of the other. Now, the third type we can look at is the one called an AND operator. And what this is a way of comparing two numbers by looking at the individual components of those numbers. So this is what we would do in a binary number, and typically this may look a little bit confusing, but a very good example of that is, for example, many ECUs have a status information where they split one byte of information, which is 8 bits, into 8 separate status numbers. So for example, if we look at this one here, this is a row of zeros, and now this one here has a 1 in that first position. So that 1 might be a status bit, which indicates, for example, that a fan has been turned on, something like that. So the reason we use this bitwise AND structure is that we might need, for example, we might have a status information that has 8 separate status values. Another good example might be an injector status, where each of these bits may represent one injector. Now, we may only wish to see the information from a certain injector, let's say injector 2, and that might be what we find here in this position here. So the operation, the design of this operation is that we have an input, which may be this status information, for example, and then we have what we call a constant, and what that does is define which of the bits is going to be used to choose a true or false output. And so in this case, we've selected bit 1, which is the second one from the right-hand end. And that means if we have a match with bit 1, we'll get a true output. So in this case, bit 1 might represent, for example, injector 2 being turned on. So if we look again at the first one, none of them are turned on. Our constant is looking for bit 1 only, so the output is false. In the second instance, we might have this 1 representing the first injector being turned on, and our binary constant is looking at the second bit. So again, the output is false. Now in this third example, for example, in this case we might actually have injector 2 turned on, and this is a match with our binary number here, so we will get a true output. And in the final case, this is something also worth noting. What the idea of the constant is to isolate which of these bits we are looking at, and it ignores the other bits. So in this case, even though both of these bits are turned on, what we have is a match with this bit, and that means we still have a true result. So in this case, we might have 3 injectors turned on, 3 fans turned on, but we're only trying to isolate one particular one and ignore the information from the others. So you can see that this bitwise AND construction is very, very useful, where we have more complicated information being carried in one byte of information on our CAN bus. Okay, so now we also have a simpler form of the AND instruction, which is the more traditional form, and that is just simply where we can combine a number of inputs and we will get an output. So these are normal logic operations which actually come originally from semiconductor logic, and what we've done is just reproduce the same functionality. And the typical AND function, for a true output, what we need is both of the inputs to be true. And so in this table we can see we have a false and a false on our inputs, and that means our output is going to be false. If we have a false and a true on our input, our output is still false, because for an AND function to be true, we need both inputs to be turned on. So as you can see, that bottom entry, true, true on the inputs, we'll get a true output. Now, an example of how this might be used, again, could be simply you may need 2 switches to be turned on before you will actuate a certain device. And if one or the other of those switches is turned on, you don't want that device to be actuated. And in this case, this bottom condition will AND of those 2 inputs. If they're both true, it will turn the output on. And the other most very common situation is where we may have 2 switches to turn on a fan, for example, and if either of those switches is turned on, we would like our fan turned on. So that's what we call an OR function. And here we can see again the same table. If we have 2 inputs that are false, the output will be false. If we have one input true, in other words, if switch 1 is true or switch 2 is true, then the output is true. That's why it's called an OR function. Same here, if input 1 is true and input 2 is false, we have a true output. And finally, if both switches are turned on or both inputs are true, then we also have a true output. So that's why it's called an OR function. It's if input 1 is true or input 2 is true, the output will be true. And we finally have one slightly more complex variant of an OR function, exclusive OR. What this means is that only one switch needs to be turned on for the output to be true, but if both switches are turned on, then the output will become false. So if we're both false, the output is false. If one of us is true, which is the same as an OR function, the output is true. But if both inputs are true, then the output is false. Now this is different from the OR function, as you can see. Again, the exclusive OR function is quite useful in terms of how your decisions are made, so that's why we've included it into these logical operators. Okay, now the second type of operator we have, again, which is extremely useful, is what we call a conditional operator. These are designed to basically to compare 2 conditions and to decide if the answer is true or false. So again, what we're looking at is an input and an output. On the top line of this display, you can see our input, and what this is a number which is stepping up from 0 down here, and it's stepping up to a higher value, and then it's stepping back down. So this could be, for example, a gear number, or it could be a temperature, it could be any of a number of things. But what we're looking at is a comparison between the number that we are using as our reference point and then what's coming in from our input channel. So a typical function here would be an equals function, in which case this is the first output here. We're showing where if we use an equal to operator, then when our input is equal to 4, as you can see on this step scale here, then our output will become true. So this, in this case, may be to turn on a fan or a relay. Now, when the input goes up to 5, then the output is false again. That means that the only time at which this condition is true is when we have an exact match between our input and what our equals to number is. Now the second one, which is also very useful, is the greater than function. And in this case, of course, if the input number is below our threshold point, then the output is false. And once that number gets over our threshold point, which in this case is 5, which you can see here on our little climbing scale, then our output becomes true. Now, obviously, as the input number goes higher than 5, the output stays true, and then once again, as it steps down here below 5, the output becomes false. Now, this is obviously it's a fairly straightforward comparison, and the most useful comparison would be for something like engine temperature, where once you get to your threshold temperature, you'd like the fan to stay on. So that's the greater than condition. Okay, we also have a less than condition, which is effectively the same as our greater than condition, but in the opposite direction. And then we have less than or equal to. So the last example we have here is less than or equal to 2. And you can see if our input number is 0, or 1, or 2, we're looking at a true output. Once our input number reaches 3, then our output becomes false because it's not less than or equal to 2. And again, later on, as this number scales back down on the other side of its ramp, once we get down to a value of 2, the output becomes true. So these are reasonably self-evident conditional operators, and they can all be combined, as we've said, but they're also very useful as an individual trigger mechanism. And these three versions are essentially all you need to make numeric comparisons. Now yet another of the operators that we have available are time and edge operators. In this case, what we're not looking at individual levels like temperatures or so forth. We're looking at a way of having a true or false input value, which then goes through either a time function or an edge function to produce an output. So the first one is our flash function, and this is very obvious. For example, if our input is the indicator switch, then what we want is when the input is false, we don't want any output, and when the input is true, we need a flash output. And in this case, we've got a true time of 1 second and a false time of 2 seconds. So at any time the input is in the true input, we have an output which will be switched on for 1 second and switched off for 2 seconds to flash. Again, that's quite a straightforward function, but it's very useful. Okay, now another time type function is our pulse function, and this function allows us to generate a pulse on either a rising edge or a falling edge on an input pulse. So for example, what we have here is an input that is false. The output is false as well. When the input becomes true, we still see no change in the output, because what this pulse is looking for is this falling edge here. When this edge goes back to a false condition, we now have an output pulse, where we've defined as a falling edge trigger and for a width of 1 second. Okay, so that will just pulse once at that for 1 second, and then it will become false again. And at some later time, we may see another input signal go true. Once again, nothing happens to the output until we see our falling edge, and then we get an exact same pulse of 1 second, because that's what we've defined. So that's what the pulse function does. Now the third function we have, which is quite useful, is the toggle function. And what this means is that each time, for example, you throw the switch or press the button, it will change the output from true to false. Now in this case, we've set it for a rising edge, as you can see here. And so let's say that's a button on the dash. I've pressed the button, I get a rising edge, and my output goes from false to true. Now when I let go of my button here, the input becomes false. There is no change to the output. What the output is doing in a toggle function is only changing state when we have a rising edge on the input. So here's our next rising edge, and then our output changes from a true state to a false state. So that effectively, in a sense, that's cutting this pulse in half. So the output pulse is half the frequency of the input pulse, but it also allows us to use a button, for example, as an on-off switch, where each time we press the button, our output turns on, and then the next time we press the button, our output turns off. Fairly straightforward. Now we also have some more complicated operators. All of these are available in each function. So um, you may or may not need to use an operator as complicated as this, but once again, they are very useful. And the hysteresis one in particular is useful for fan control. What hysteresis allows us to do, rather than have a greater than or less than number which is fixed, it allows us to have a greater than number, for example, to turn the channel on, and a separate number to turn the channel off. And this is typically used again with something like an engine fan. So in this case, we've set 70 as our on point, which is right here. And so as for example, our temperature is cycling up and down, nothing's happening. And then when we get to the point at 70, our output becomes true. In this case, that might be something like a fan. Now, when this temperature drops below 70, you see that the output is still actually true. What the hysteresis function allows us to do is set a separate number which turns that output false again. So once our temperature gets down to 40, which is where we've set our low value, that's when our output becomes false. Again, this is fairly typically used for engine fans where you might turn on at 105 and turn off at 98 or something like that. Clearly, if you had a fan that turned on and off at exactly the same temperature, it would just be continuously cycling as the cooling. So we normally use hysteresis in these sort of fan devices. Right, now the other type of logic function we have which is extremely useful is a set and reset function. Now what this involves is having two inputs into a logic function, one of which turns the function on, and then a separate input which turns the function off. So for example, you may have a button that turns headlights on, and you might have a separate button that turns headlights off. Now this in itself doesn't sound terribly useful, but when it's combined in various other logic forms, it's extremely useful. So when the function is false, as in this case, if I set the reset function to high, it has no effect because we're already in this false condition. When my set input goes to true, that's when my output is true, and it will stay that way regardless of how many times I press the set condition or the set condition goes to true, because that is only designed to turn the output on. When my reset logic level goes to true, that's when the output will go to false. So in other words, the input for set input is what turns the output on, and the reset input is what turns the output off. Now the other operator we have which is extremely useful is time filtering. This is something we can use to introduce delays or to slow down response times to conditions, and that allows us to again, we can use this in something like fan control, or another typical use might be for an oil pressure switch. Let's say we have an oil pressure switch that goes off at a certain pressure, and in the case of the particular engine, every time the engine idles, we see low pressure on the oil pressure switch. This is quite common on a lot of engines. Now, we don't necessarily need to see an oil alarm going off in our dashboard or engine ECU, because when the engine's idling, we're not terribly concerned about what the oil pressure is. So one way we can get around this is to simply put a delay on that oil switch for say 3 or 5 seconds, so that it will only turn on if the oil pressure has been low for a certain amount of time. So here we have a true-false condition where the input goes to the true condition, and then we have a 3-second delay before the output goes high. And we can set a separate delay for the false condition, so the input goes back to false here, and then 1 second later our output goes low. So this is quite a useful way to tailor the way our indicators are working, and or how we're driving like relays as well. All right, so what we've seen is all of the various forms of operator and condition that are available as individual components. But the other great benefit we have with this system is that we can combine these into a very complicated logic function, and they're all interactive and they can all refer to each other. So what we've got here is a not actually terribly complicated function, but what I'm going to do now is go through how we would create this function step by step. This may not be something you would ever need to do on your particular vehicle, but it serves as a good example of what the what the individual operations are when you are using the PDM Manager software. So what this function does is a way of running a cool down fan, and we typically would want a number of ways to run this fan. Firstly, we want the fan to come on when the engine temperature is too high. Secondly, we may only want this fan to be operating while the car is actually on the track. And thirdly, we may only want the fan to be operating when we have a certain number of RPM. And that typically means when you can come into the pits, we don't necessarily want the fan to be working and draining the battery while you're in the pits. As soon as you get back out on the track, pardon me, it may be quite beneficial to turn this fan on under these conditions. And the last thing we've got here, in fact, is a cool down switch, because the other thing that can happen is when you bring the car in, you may want to keep this fan running, and you can have a switch on the dashboard. For example, when you're finally going to pit or it's the end of a session, you just throw that switch, and this will allow the fan to stay on even though you no longer have any ground speed. You may still want the fan to stay on for a couple of minutes just at the end of the session. So all of these logical operators can be combined to produce this one function that drives the fan. And just to repeat all that again, so we have two possible scenarios. On the top, we have three scenarios that need to control the fan more or less when the car is out on the track. And on the bottom, we have another scenario, which is perhaps when the cars come into the pits at the end of the session. So we want all these functions combined here with this AND function. And then we want that composite to be ORed with this composite. And what that means is that if either one or the other of these conditions is going to drive our fan. So now I'm going to go through step by step and just show each of the individual button clicks in our software that it will be required. Now, some of this is a little bit repetitious, but the reason we're doing it in this webinar is so that you can replay it later and you can see each individual step and then what you will be seeing on your own screen on the PC. I should also point out that you don't need the PDM connected to be able to replicate what I'm going to show you now. You can just use the software which you can download from the website, and you can run through exactly the same process, and that may be a useful thing to try, just to give you some familiarity with setting up these complex logic functions. Okay, so the step-by-step process. Firstly, what we need to do is we need to set up our engine temperature trigger. So what we've got is I've already built a PDM input system that has engine temperature and ground speed and engine RPM coming in as inputs, and also a cool down switch input, so we don't need to go through that. Hope you've already looked at our PDM webinars to have basic functionality with a PDM. So if you haven't done that, I suggest you go and have a look at those webinars, and that will show you how we build inputs and so forth. But so we're just assuming that those inputs are already in this PDM, and what we're now going to do is look at building each of these triggers and then combining those logic functions. So the first thing we do is we click on the conditions entry on the left-hand side there, and then we're going to add a new condition. So when I go over into the right-hand side of this screen and I right-click and I click on the Add Condition option, and that will open this dialog box that you can see here. Now, one of the great things about the PDM is that you can call these functions anything you like, and I've decided to call this one the engine temp trigger. So what that means is I could call it engine temperature trigger, I could call it engine trigger. That would be a little bit vague. The point is we need to have a plain English description here, and you can name that condition anything you like. So we've called it engine temp trigger, and then down below where the condition is, it shows that same name. And then for us to define what that trigger involves, we click on this Add button here, and the next screen will show us the screen that opens up when we hit the Add button. Okay, so now the Add button allows us to define how this operation is to work. And the first thing we need to do is this first option at the top, and that's what we've selected here is a hysteresis function, as we described earlier. For something like engine temperature, we need to set two different temperatures, so we use the hysteresis function. So all you do is you click on this pull down here, and you select hysteresis out of your possible logical operators. Then the next thing you do is you go to the channel input, and you click on this selector on the right hand side, and you select your engine temperature channel, which has already been into the PDM Manager. I'm not going to show you how to do that here. So we select engine temperature, and then we select our active high level, which means that when the output is true, when these conditions are met, the output will be true. And then we enter in our two threshold numbers. The result is true when the channel is above 90, and the result is false when the channel is below 85. So these are just two temperatures that allow our hysteresis band to be set. So once we've done that, then we hit the OK button, and what you'll see on the next screen is that we now have these conditions showing here. So it now says engine temperature trigger equals hysteresis, engine temperature, active high, and then it shows the actual temperature numbers as well, which are actually clipped at the moment. But the point is that that now shows that we've defined how our engine temp trigger is going to work. Now if we just hit OK on that button, this is the OK button here I should say, what that will now do, see here, we've now got this in our conditions. So I had some other conditions in this PDM file already, and it's now added our engine temp trigger condition. And you can see here it's fully listed, again, the way it was in the previous screen, but now you can read each of these parameters. High equals 90 and low equals 85. So now that's in part of our conditions list. Now we need to do the same thing for our ground speed and our engine RPM. I won't go through these in detail because the process is the same, but I'm just going to show you each of these screens, and that means if you want to do the same thing with your PDM Manager software, you should be able to see the same thing happening. So the next thing I do is in my empty space, I right click and I say add condition. Okay, now I'm going to type in the name, which I've called ground speed trigger. We just use this term trigger as a useful way to separate our logic functions. So now down here I have my ground speed trigger, and then I click on my add button. Again, this is the same process we've just done for the engine temperature trigger. I click on my add button, and then I can choose the operator. In this case, the operator is less than, because we want something where if our speed is above 60 kilometers an hour, we have a different output. So we select our less than operator using this pull down, then go across, we select ground speed, put in our number, our constant, which is 60, and then we press OK. Okay, now again, I'll just go quickly through this. So now we can see down here in our ground speed trigger, that's showing the information we've just entered in. So we click OK again, and then we see our ground speed trigger has been added to our list of conditions. So we now have our engine temp trigger and our ground speed trigger as two separate trigger conditions that we can use. Next, we need to build our engine RPM trigger condition. Same thing applies. You right click in the blank area and hit add, and you then add another condition. I've typed in the name engine RPM trigger here. Then I click on the add button. Then it opens into my properties screen. So the next thing I want to do is my engine RPM needs to be greater than 500 RPM for 5 seconds, or it needs to be less than 500 RPM for 10 seconds. So my operator here I've chosen is greater than. My channel is engine RPM. I've chosen a constant of 5. I won't explain this in detail, but 5 in this case represents 500 RPM. That's a separate issue which we don't need to cover at this point in time. Then down below, because I've used this greater than function, I can actually use these delay numbers. Now you would have seen on our previous examples for ground speed and engine temp, we also had delays, but I set them at very, very small numbers. In this case, because I effectively wanted them to be instantaneous, in this case I'm setting my turn on for 5 seconds. We need to be over 500 RPM for 5 seconds. And then I've set my turn off time for 10 seconds. We need to be under 500 RPM for 10 seconds. So then again, we click the OK button, and we can now see our engine RPM trigger. In the bottom box, you can see what those conditions are that we've just set. So then again, we click the OK button here, and that will now show up in our list of conditions. So we've got our engine RPM trigger. Same thing applies to our cooldown switch. Again, I don't need to go through this in detail, but just to show you each of these screens, cooldown switch trigger is the name I've typed in. Then I hit my add button. Then I get my conditions screen. In this case, what I'm looking for is a pulse, because I want the thing to pulse for 120 seconds after I turn that switch on. So I select my pulse as my logical operator function. Then I go on the rising edge, which means as that switch is turned on, I use my cool down switch as my input channel, and I select 120 seconds as the amount of time I'm going to keep this pulse active. So then I go down and I click the OK button. Again, we can see this function now displayed in the bottom here, so we know that we've got the right thing. And then finally we click OK, and this also appears in our list of conditions. So we've now created each of these 4 conditions, and what we next have to do is combine these conditions using these AND functions and this OR function here, and that's what will give us our final output control for the fan. So again, the next step we need to do is to combine each of these separate trigger conditions into our output channel control. So I've called this condition our fan output control, and down in my bottom box it's still empty because I need to add my conditions in. So in this case, I'm going to add these pre-designed conditions that we've just used, and that way I'm going to create a complex logic function out of a series of simple logic functions. So I click my add button. Once again, we get our properties screen. The operator is just a simple true false type operator, and now I select my engine temp trigger, which is one of the ones I've just created. And in this case, I don't have any delays. I've set a very short delay of 0.02 seconds, which just means as soon as my engine temp trigger is true, this function will become a true function. Hit my OK button. And now you can see in the fan output control, we have added engine temp trigger. Now we need to add the others. So we just click the add button again. And I'm going to add the same type of trigger, which is a true trigger, and I'm adding my ground speed now. Same sort of setup. Just click here, select ground speed trigger, click OK, and then we now see we have engine temp trigger, and this is the critical thing here, the fan output control, engine temp trigger here, and ground speed trigger here. So that's what we're seeing here is this AND box here. Right, now obviously we still need to add our engine RPM trigger to that AND box. So again, I go over and I click on my add button. I get my properties screen. I'm looking for a true false property. I select on here, I select my engine RPM trigger. I click my OK button. And now I'm going to see all 3 of these conditions all grouped together as one large AND function. Now, the other function we're looking for is this cooldown switch input, and that's via the use of an OR function. So what we've done is we've created those 3 blocks that are in that AND there. Now I'm going to create this OR function here. So if you look across onto your condition box, we've got an OR. I click on this box here, then I click the add button, and then it allows me to enter my cooldown switch parameters. Now you can see, if we look across at this logic diagram here, the cooldown switch goes straight into there, but it also goes through this rising pulse delay. So we need to actually add both of these into this AND state. So my cooldown switch is just a straight input from the switch. I add that, I click OK. And now you can see we have our first AND function at the top, and we have an OR here, and we have our cooldown switch at the bottom. And we now finally need to add in the cooldown switch trigger, which is this rising pulse. So I click on my and I click add, and then I add my last function, which is my cooldown switch trigger. Now this may all look very complicated, but the point here is we're building it up one block at a time. So once when I click on my OK button, now I can see my full logical composite, if you like, and we have the top section here showing the first 3 conditions, and then the OR function, and then the bottom showing the last 2 conditions. So we've created a very complicated mixture of logic conditions to drive our fan output. So then we just click OK, and that will appear in our overall logical operator list. And then the last thing we need to do is we need to actually get this new logical operator to control our fan. So what we now do is we go up to our screen on the left, we click on our output pins, we create an output channel, which we've just simply called fan, because that's what we're trying to do. And the only thing you need to note here is that we've used a fan channel here, and then down the bottom, I've got the output is active when the following is true, and I've got a channel here, and now I've selected using this button, I've selected that fan output control, which is that logic operator that we've created. So we've combined all of these logic functions into one complicated logic operator, and now we've selected that complicated logic operator to turn our fan on and off. So then we just click on our OK button, and that would be the end of our setup. Now I realise we've gone through this fairly quickly, but you can see that each of these steps is quite similar, and what we've just done is built a series of logical blocks, and that's combined together to give us a complicated logic function. And we've used obviously a number of different types of these logic operators just as an example of how they might work together. So that's all we're going to talk about today. We do have further information available. Firstly, this webinar has been recorded, and that means you can download it off our website. All you need to do is go to the address you can see on your screen, to the webinars address. And of course, we do have our Motec forums, which are a very useful way to interact with other users of our products. And these forums are broken up into multiple topics. So you can go, we have a PDM forum, and we also, of course, have ECU and dashboard forums. And so this is a great way to share anything you may have found, or to ask other users if they have any help. Now, all of our support staff here at Motec in Melbourne pay a lot of attention to this forum, so you can always put something on the forum and answer. If not from one of the other Motec users, you get an answer from one of us here at Motec in. Thanks very much for attending. I hope I haven't taken this too quickly, but the whole point here is to show the simple step-by-step process whereby we can build very complicated logic functions. That's the end of this webinar. Thanks very much.